this video, we are going to be looking at Newton's laws of motion. So as we move forward, I would like to review Newton's first law of motion, which we had covered in class. So essentially, as you see in this graphic, Newton's first law states that if forces are balanced, then that means you get two different situations. Your objects are either at rest or your object is in rest in motion. But if the forces are balanced, then the result means in either situation that you have zero acceleration. So if your object is at rest, the object will stay at rest. If your object is moving, then the object will continue to move and at a constant velocity forever, unless acted upon by an unbalanced force. We illustrated this with the index card and the penny, the tablecloth with a textbook, and then the dishes sort of trick. And we even showed something like this with a penny atop a hoop, all demonstrating the first law, also known as the law of inertia. Inertia being the tendency of an object to resist a change in its motion. So as we move forward, we want to take a look at Newton's second law. Newton's second law is very interesting because it picks up where the first law has left off. So the first law says you need an unbalanced force to cause acceleration. The second law states very specifically what that acceleration causes. So as it says here, the rate of acceleration depends upon two things. One, the size of the force. The harder the push, the greater the acceleration. The other thing that acceleration depends on is the mass of your object. So the more mass of your object, the less your object will accelerate. Mathematically, we can write that as A equals F over M. So we want to illustrate that. So if you take a look at this drawing that you have here, notice it shows a person with a golf club. So imagine the size of the force that a person can put on a golf ball using a golf club. So that force is illustrated here with the letter F. And you notice the size of the F. So the person takes their swing with their golf club and they strike the golf ball. Now a golf ball is not a very massive object. So imagine, with the force that you can apply to a golf ball, the acceleration of that golf ball is rather large. So you'll notice in this graphic the rather large A. The result is a great acceleration because of a small mass with a sizable force. Now let's do something different. Let's take that same exact person, same exact swing, same exact golf club, but instead of striking the golf club, use that same exact force and strike this truck. Okay. Imagine what the difference is. You strike that truck, and even if there's no friction whatsoever between the truck and the ground, assume that the truck is in neutral. Assume it's on the most slippery ice possible. Still imagine what happens when you strike a truck with a golf club. I don't recommend you try this at home, by the way. But think what's going to happen. The truck is so massive that the resulting acceleration is going to be tiny, tiny, if you even overcome the little amount of friction that's there at all. Who knows? The truck may not even move. If it was a completely frictionless environment, it may move, but just at a tiny, tiny rate. So you notice in this diagram, even though the force is the same as in this situation, you'll notice that the mass is so large that the result is a small acceleration. We can put this another way. I'd like to show you this simulation. This is linked on our web page. So as we go to the web, you'll notice that it says click to select a person, then to select a car. So if I pick this person here who's going to push with a force of 10 newtons, and you notice that the force gets added to my equation. And let's say they pull on a grocery cart that has a mass of 10 kilograms, then you'll notice that the result, 10 newtons over 10 kilograms, would result in acceleration of 10 over 10, which would be 1 meter per second. Now that's an acceleration. Notice the spacing of the dots. As time goes on, that person's velocity velocity is increasing by 1 meter per second every second. Take that same person, but apply a force to an object that is twice as massive. So we have a object that is 20 kilograms. Now I get 10 newtons over 20 kilograms, and I get an acceleration that is half as much, 0.5 meters per second per second. So what this is showing is if my force is constant and my mass increases, then my acceleration gets smaller. Big mass, small acceleration. If we reset this and go back to our golf club example, imagine that I keep the size of my object the same. So I keep it at 10 kilograms of mass. But I apply a force of 10 newtons. As we stated before, the acceleration will be 10 over 10, which is 1 meter per second per second. But what if I double my force? I push twice as hard on the same exact object. So instead of 10 newtons, I'm going to push 20 newtons. Well, the result is 20 newtons over 10. My acceleration is going to be twice as much. Or in this case, instead of 1 meter per second, 2 meters per second. What if I quadruple my force? Instead of pushing with a force of 10, I'm going to push with a force of 40 newtons. I'm going to push with that force of 40 on something with an object of 10 kilograms worth of mass. So now my acceleration is quadrupled. It is 4 meters per second per second. This may not seem all that important, but you have to remember that this was the first law that really governed and said specifically exactly how much acceleration that you would get after applying an unbalanced force on an object. So in conclusion, Newton's first law, objects will not accelerate unless acted upon by an unbalanced force. Newton's second law, that force causes acceleration. The rate of that acceleration depends upon the mass and the force applied. As stated on this page here, the second law of motion states that a force will make a body accelerate by an amount that is inversely proportional to its mass. That means as mass goes up, acceleration goes down.